Now onto the product rule. I had said in the previous video that the derivative of a product is not the product of the derivative. Now it's actually easy to see this, not only with a simple example, but just if you look at the difference quotient. This is the derivative of product, and if I do the product of the derivatives, let's just write it down. So if I have fg, I mean f of x times g of x, right? So if I write down what this actually is in terms of the definition, it's f at x plus h, g of x plus h minus f of x, g of x over h. Whereas if I write down what this is two different limits, right? This is two different expressions. One of them, let's see if I can have enough space to do this. One of them looks like this, and the other is the G one, right? Now it's true, it's true that if both of these limits exist, I can pull out the limit on h and take it all at the same time. But what's going to happen when I multiply these two? I'm not going to get this. I'm going to get some expressions that look kind of the same, but it's not. But there's some bunch of cross terms in here, and this f of g is going to have the wrong sign. Anyway, this is just not going to work. They're not the same. Okay? And you can certainly see that, for example, if we take, knowing what we know, the product rule, we can easily take some function like x cubed and sort of break it up into two smaller ones, x squared times x. And if you do the derivatives, you'll see that they don't work out. So what is this? Okay? And we need to know this because there's lots of different functions that we have that are derivative, that are multiplying different functions, and then we need to take their derivatives. So I'm not going to prove this because it is a somewhat of a lengthy proof that I will put the proof in the extra materials for you, for those who are interested. But there's also a more geometric explanation done by 3 Blue 1 Brown that's also in the extra materials. So you might want to look at either one of those or both, either the analytic proof or just kind of watch the video to get a sort of a geometric feeling for what's going on. But this is the formula. Basically, you take the first one times the derivative of the second one, and you add it to the second one times the derivative of the first one. Okay, so you gotta mix them up a little bit. And that's the way it goes. You can remember it this way. If with the prime notation, it looks like this. Something like that, whatever. I think I wrote the wrong way. I have to just write the same thing, right? So it should be like this. To be honest, I tend to not use F and G. I tend to use U and V. You'll see also when you get into Calc 2, we use U and V a lot. And then later on, with just next week with the chain rule. So it's not like it matters that much. But just in general, I will occasionally write, if I write this, I do tend to default to using U and V. U dv dx plus v du dx. So with those letters instead. But whatever you want to use, it's fine. You don't really even have to write down the rule. And once you start using it, you'll know it pretty well. Just a question of practice. So, for example, let's differentiate x squared e to the x. Okay? So, if I'm using this rule, it doesn't matter which one is which. I can pick u is x squared and v is e to the x. That's what I had. V equals e to the x. And I'm just going to write it. I'm not going to rewrite the rule. I'm just going to write this times the derivative of that. So x squared d dx of e to the x plus e to the x d dx of x squared. And I will do these this way in a two-step process pretty much always. Very maybe towards the end, you can do this in your head, but definitely now write this down as one step and then go through and evaluate the derivatives. That way you won't mess it up and you won't lose any. Okay, so here I've got the derivative e to the x is just e to the x, and the derivative of x squared is just 2x, so this term becomes 2x e to the x, and I'm done. That's the derivative of that. You will see that using this, you will get a longer expression, right? It's not as nicely compact as the power rule because you're multiplying, so it's just going to get big. That happens. Sometimes, all right, let me actually do another example. Sometimes there's this one you can just do this way. There's no other way to do this because I've got e to the x and I'm multiplying by this x squared, and this is as simple as that is going to be. Sometimes you do have an option for either doing some simplifications first or doing the power rule, or doing the product rule. And let me give you an example of one where we can do that, and I'll do it two different ways. What do I have here? Y equals 2x squared minus 3x times the cube root. That's a cube root. Sorry, guys, didn't look good, but a cube root of x. Okay, so I've got this guy times that guy. I go ahead and use my power, sorry, I keep saying power rule. I mean my product rule. I'm going to pull it over here so I have more space. So I have 2x squared minus 3x times the derivative of that cube root, which I'm going to write as x to the 1/3 because, of course, I need to use the power. Now I can say power rule on that, right? And then I've got x to the 1/3 times the derivative of 2x squared minus 3x. Okay? So that gives me 2x squared minus 3x times 1/3 x to the negative 2/3 plus x to the 1/3 times 4x minus 3. And then I can do some algebra to clean that up, because then combine like term stuff. I'll do it in a minute. Before I do that, I want to point out something else, though. Instead of having done it that way, I could have first simplified this, right? Because I could have written this as 2x squared minus 3x times x to the 1/3. And then I could have just pulled that guy right in there. So this would have been 2x to, okay, and remember when I multiply things with exponents, I'm adding the exponents, so I want to do 2 plus 1/3, right? So that would be 7/3, right? 6 plus 1 is 7. So I get 2x to the 7/3 minus 3x to the 4/3 when I multiply that guy through. Now this is a straightforward power rule problem. Now I no longer have to use this product rule. I just go like this, and I have 2 times 7/3 x to the, 7/3 minus 1. So 7 minus 3 is 4. And then 3 times 4/3 x to the 1/3. These 3's cancel. If I make this a little nice here, I get this. Now, they don't look the same, right? But are they the same? I can work this out and we'll see. Okay, again, that's what I've got here, 2/3, and then this would be x to the 2 minus 2/3, so 6/3 minus 2/3 is 4/3, minus x to the 1 minus 2/3 is 1/3, because the 3's cancel. Then here I've got plus, wait a minute, what's happened here? Well, let's just, yeah, okay, yeah. So, okay, well, 4/3, that's right. 4 times, again, I've got 1, so this is 4x to the 4/3, and yeah, then I have 3x to the 1/3. All right, now, if I add these two, I've got 2/3 plus 12/3, so that's 14/3. X to the 4/3 minus 4 x to the 1/3. They are the same, okay? So sometimes it may be easier to simplify first. Sometimes it doesn't matter. It's the equal amount of work depending on the form. Sometimes you don't have a choice. You have to use the power rule.